Hello, and welcome back to another video with It's Dr. Dan. And today we're going to be doing a lecture on hybridization. And I say the word mini up there, but that's probably a little bit misleading because this video is going to be a longer one because we're going to be going through all of the theory and the practice of using hybridization. If you're interested in going straight to the practice problems, fast forward through the video. I put in chapter markers on the YouTube video so you can go directly to it. So that way you can be able to study directly the things that you need to know for how to do an exam. However, the best way to be able to understand anything to tackle any problem is by understanding the theory behind it. So if you're someone that's just trying to cram, I would recommend you actually listen to all the little details. So where's it really starting? So we're going to just understand the basics of covalent bonding. So it starts all with valence bond theory, which is we look at the valence electrons and we're specifically looking at the outermost layer of those electrons and how they're all situated in the individual atomic orbitals of the atoms. Now, when the little atoms get close together, their orbitals will overlap slightly and they can share electrons, especially whenever you have a half filled orbital. It can create a pair between both of them and we can share an electron. And that sounds all great, right? That's how we learned it in high school chem. And that's how we've described it, since even Chem 3A or all the basics. So, how's that work? So, let's say if I have like a hydrogen atom, it has a 1s1 electron, so a single electron. So the way that you generally would draw it, right, is you would draw that s orbital. It would have one little electron in it. You draw another s orbital. It also has one little electron, and we would overlap them, right? So as they overlap, it's going to make a pair between those two. So we can make a pair between an s orbital and an s orbital. Great. And there's a lot of overlap there, so it's a really strong bond. What else could you have? Well, when we're looking at this, we're thinking of, all right, what's the last lonely electron in the valence level? So, back to hydrogen. All right, it's 1s1. All right, so then if you think of, all right, fluorine, well, okay, what are its valence? Well, it has 2s2, 2p5. So it has one electron in the p level that does not have a partner. So, all right, if we want to have another overlap, you can have the s orbital, and then you can draw a p orbital, right, interacting with each other. So you got s and p, and they can interact and make a really strong bond because there's a lot of overlap on the end of that, right? So we have a little dot on both orbitals and they're both being shared and we can make a bond, right? Same thing if I have my two fluorines. Well, all right, well, we just talked about the orbital, right? The last orbital for that's another p orbital. So if we have it where, let's say we draw a p orbital from one fluorine and then we want to do the p orbital from another fluorine, well, they can overlap with one another and we can have a P to P type of interaction, right? So it's all about those orbitals fitting together really, really well, making a very strong interaction. And that's what we're going to be diving into, is because the more you think about it, there's a lot of little things that probably never really made a lot of sense, and your teacher probably glazed over it a little bit. Let's kind of dive in a little bit more. So specifically, when a covalent bond is formed is when two orbitals are overlapping. Now, in order for this to work, right, the following cases need to be in play. The orbital of one atom has to overlap with the orbital of the second. The next thing that was always at play is that each one has to have a single electron from each one in order for them to both be shared. Now, it's not only the electrons that we have this pair, right? You have to remember that the entire thing is that there's an attraction between the electron and the positively charged nuclei, right? And that's where that overall interaction is going to happen. So the more overlap we have, the stronger the bond. So the ones I mentioned above are the ones we're looking for, right? S to S, SP, P to P, right? It has to be one of those. They have to have a lot of overlap. And if they don't, well, it's not going to be that strong of a bond. So whenever we have this strong bond of SSPP or SP, this is what we call a sigma bond, right? This is the beginning of a single bond, right? How to interact and overlap that. So, okay. So how would this whole entire thing work? So let's say if I had a carbon bonding to another carbon. Well, if we were to look at it in the traditional sense of valence bond theory, we would first fill in our valence electrons and we see, okay, we have these two electrons that are all alone for carbon. So, okay, it can make two bonds. And you're like, wait a minute, I thought carbon makes four bonds. I thought that was one of our bonding trends. And you're right. So there's some problems with this theory already, right? We have to be able to fill in the entire things. Okay, but let's just play along, see what kind of bonds we can make. All right, so we have these two little electrons up here. They can make two bonds. So what kind of bonds can they have? So the first one is all about that sigma bond. So, okay, we're going to draw our p orbital, right? It has those double lobes, and we're going to overlap them, right? So just like so. All right, this is what we call a sigma bond. There is overlap with these, right? Now, the next one that's possible is, let's say if this wants to bond a little bit more, is you can create a pi bond. So, okay, we just drew the px orbital, right? So it's going along our x-axis. So we can also draw like a py orbital or even a pz orbital, going on our Cartesian axes to show all the different possibilities of parallel. But right now, our atomic orbital only shows that we just have two. So, all right, we're going to go along with it. Okay, we see that these two red ones, they're both parallel with one another. And what's going to happen is that these orbitals are going to overlap with each other and make a very diffuse orbital behind them. All right, so this is our pi bond. Now, when I say diffuse, this matters because this refers to the strength, right? You see those sigmas right here, right at the middle, are overlapping completely, right? You see that? So they're really close together. Whereas the pi's, they kind of got to stretch in order to be able to kind of reach in that general area. So sigma is stronger than pi, and it's going to lead to a stronger overlap. So that's some things to keep in mind as we move forward. So, okay, let's try to see if we can dive into why we can't make four bonds or go farther in this. Okay, so clearly we're missing something. Let's look at another example and see if we can really spot where the problem is. So, okay, one of the things is water, right? One of the molecules of life, one of the ones we have to understand completely. If you were to study water, right, and you were to actually look at the bond angles with water, one of the things about it is that what you would find is it's roughly around 104.5 degrees. Great. That's what Vesper theory says. That's what actual data says. Let's see if it makes sense based on what we know of orbitals. Okay, so if we look at the valence levels, right? So we look at 2s and then we look at 2p. We know that it has 6 valence electrons. So we got 1, 2, 3, 4, 5, 6. So we can make 2 bonds. Fantastic. That's exactly what we want. So we're going to be combining with those 2 hydrogens. So, all right, we'll put them in our 2 of our axes. So we're going to make one orbital that's on the y-axis. We're going to do another orbital that's on the x-axis. And that's going to be bonding to each of our little hydrogens. Okay. So, all right, we're going to put one hydrogen on one axis. That's going to bond to its s orbital. Then we'll put another hydrogen on the y-axis. Great. So we put all that there. So we have this P to S interaction. That's exactly what we want. But wait a minute. If I'm looking at X and Y Cartesian axis, what's the bond angle that's here? This is 90 degrees. That doesn't explain what data shows. So it's not matching at all. That's a problem. So we need something more, right? We need to know about how the entire picture, right? So valence bond theory needs something extra. This is where quantum mechanics comes in, right? And all of our eyes glaze over like, oh God, not again. So one of the big equations from that was this guy. It's the Schrodinger equation, which H psi is equal to E psi. Now, the psi function, this is the most important part, is because this is known as the wave function, which gives you details on where the electron is most probably located, right, around its orbitals. So it gives you information about the orbitals. Now, it works really well for isolated atoms. However, when two atoms get a little closer together, well, they interact with each other and they change the wave functions as a result because you have two different things interacting with each other. Same thing as you were to talk to somebody and have an interaction with them, right? Your feelings towards them and how you think about them is going to change. Meaning that every time you see them, maybe you'll get excited, maybe you'll be like, oh God, not again. You're going to have a reaction. So the wave function changes as it comes into contact because it needs to bond and it wants to try to space everything out to be in the perfect spot, right? So low energy, low anxiety. It wants to include everybody. So what's going to happen is that wave function is going to change. It's going to lead that atomic orbital is going to make a new shape, a new hybridized shape. Now, what's going to happen is all the orbitals that are taking apart and bonding are going to kind of add on top of each other. It's going to make a combination of all of them together. So this is what we call a linear combination of atomic orbitals. Now, depending on your course level, you might need to know the exact details of this. Usually it's not until your junior year when you're taking physical chemistry is when you need that. But for Gen Chem, all we need to know is that this is called hybridization, meaning that those atomic orbitals are going to change their shape to fit the Vesper geometries. So they're going to orient themselves so that way it pushes everything to be equidistant, changing into this new shape to be able to talk about bonding. All right. So how does this entire thing kind of work in terms of hybrid orbitals, right? How does that really change? Okay, so our head's probably spinning a little bit. So we have these new orbitals that we're talking about. So first thing, right, is talking about oxygen. Okay, so oxygen had those 6 valence electrons. So that's what we're talking about when we talk about a isolated atom, right? It's not interacting with anything. It's just by itself. Nothing changed. However, we need to be able to calculate hybrid orbitals, right? So it's pretty easy to do. The big thing is that these hybrid orbitals have a set labeling, and it's equivalent to your electron groups from Vesper or your steric number, whatever you might call it. So what happens here is, well, okay, so in water, what did we see in the Lewis structure? Well, okay, so water bonds to two hydrogens, right? So our oxygen bonds to two hydrogens, and we have two lone pairs. Okay, so two lone pairs, two hydrogens, that's a total of four groups, right? So if we have four groups, we need four hybrid orbitals to connect to those four groups. Okay, it's going to be the entire idea. And if you're like, I don't remember what water looks like, here you go, right? You see those four individual groups, and if that revolve around your geometry. Okay, so we have our original shape, right? So when it comes to our isolated atom, nothing changed. But being that we need four groups, what is going to happen is we need to change those four orbits where they're going to be essentially relaxing down. So the p orbitals are going to relax down. The s orbital is going to get a little bit excited. It's going to be kind of like an average in between of the energy. So four atomic orbitals go in, four hybrid orbitals come out. So the way that works is s is going in, and we have the three p orbitals, right? So being that we had the ones from 2p on the left here, we have all three of these. So we have all this little character being added together, a little bit of s and the three p's. So, okay, what can we call this guy? Well, let's be original, right? Let's call it SP to the third power, being that, hey, SP3, being that we're combining a little bit of each. So how do we fill in the electrons from this? Well, we're going to do the same thing we always done with electron configuration. We had 6 electrons. We're going to fill across because they're degenerate with one another, all the same energy. And what does it tell you is, ooh, this gives you some interesting information. It shows you, hey, you have room for 2 bonds, and you can show the 2 lone pairs, and they're all equivalent to each other when it comes to their energy. And that's what that's showing when you look at that Lewis structure above. It helps explain the entire picture. Whereas before, it's like you had a random lone pair on a lower energy level, one on a higher. There's these bonds. It's like this kind of weird. Like I'm just listening to my instructor and just filling it in. What does this kind of tell you is that, okay, one is that it tells you that you have this 25% of its S character, 75% of its P character. So it's lowering the energy of these orbitals, and it's giving you this brand new shape, which is going to lead to the tetrahedral geometry, or all these different Vesper shapes. So let's dive in a little more. All right, so when does this work? Does it work all the time? All right, so for this to hold true, right, this has to be able to predict chemical and biological behavior. That's the most important thing, right? If it doesn't predict behavior for chemicals, it's a useless theory, right? It has to be able to predict it. And this is something that helped be able to shape how we understand the structures of major proteins, DNA, all these kinds of molecules. It's what really led it to it when it was first discovered in around the 1930s, or understood when Linus Pauling first started to come up with this theory to describe these things. So the whole idea here is that hybrid orbitals do not exist on isolated atoms. They have to form a bond. Okay, so now is this every bound atom? And the sad thing is, no. It has to form at least 2 or more bonds for this to happen. So if you see something where once you have that steric number is equal to at least 2, then it can occur. Same thing applies to anything that makes a double or a triple bond as well. They will also hybridize because it's all about trying to place the electrons in the most relaxed possible way. So now what about the shapes and the orientations? Well, they're similar to SPD and F, but it's a combination of SPD and F, meaning it's going to make a whole brand new shape. So essentially is that whenever you have these atomic orbitals going in, you're going to have a set of hybrid orbitals that are going to be generated as a result of that. So what is that kind of telling you in normal words? So let's say if I have steric numbers equal to 3. So I'm bonding the 3 groups. That means I need 3 atomic orbitals to make that happen. However, it needs to lower its energy, so it's going to create 3 hybrid orbitals. So 3, 3, and 3 all across the board. Same thing if I had a steric number of, let's say, 5, right? So I have 5 groups I need to attach to. So I'm going to use 5 atomic orbitals, that are going to start interacting with things, and they're going to convert into 5 hybrid orbitals. They're going to change. Is going to be the whole idea there. Now, when we create these hybrid orbitals, they're all the same energy, right? So it's somewhere in between your original atomics. So if you have like 2 atomics that are like here, your hybrid is going to be like right in the middle of those, right? It's the whole idea. So then they're going to be the exact same shape and the exact same energy, which is going to be good. And they all add together, right? Now, the other thing is too, like if you don't have to be an expert at all these things above, is because they're going to make the shape of your geometries. So if you have a Vesper chart or you're memorizing and starting to learn it, it's going to match that. So it's not, not the worst thing ever. It's going to be the exact same thing. Now, what else is there? Well, in terms of how do you kind of fit all these things, what goes in hybrid orbitals, what doesn't, because that's probably the hardest part. So when it comes to a sigma bond, right, that's a hybrid orbital. Same thing with lone pairs. So they both go in hybridized orbitals because that's what determines how many electron groups you have, right, around all the central atoms. That's like the base layer. Now, the double bonds, whenever you have a double or a triple, this is when we'll use our unhybridized orbitals, meaning your original orbitals. So usually it's p or maybe the d orbitals to do that. Now, for whenever you have single, double, and triple bonds, it's a combination of all these working together. Because remember, every orbital holds 2 electrons. So if you want to do a single, it's just going to be sigma. If you want to do a double, well, you need 4 electrons, meaning 2 orbitals. So sigma is going to come in, and a pi orbital. If you want a triple, it's going to be sigma and 2 pi orbitals. So it's be 3 orbitals all together, working together. And that's going to be kind of the whole idea, right? And that's one of the things I'd highly recommend you write down. So that's going to help you be able to figure out all those little details. Let's go on to our how-to guide, right? And that's probably where if you're like trying to figure out like where to kind of watch and you just want to watch a shorter video, if you're fast forwarding around, this is where most likely I'm going to be doing that with the editing. All right, what is the how-to guide for all this? What's the short and sweet version? So when it comes to this, how do you assign hybrid orbitals around your central atom? So as I said before, if you want to watch the theory, rewind or go to my full version. For the short version, all you're going to do is you're going to determine your Lewis structure, just like you've probably been doing for a couple weeks now when it comes to all doing that. You're going to determine your number of electron groups, right? Or your steric number. So meaning you're counting how many atoms and lone pairs there are around your central atom. Then you're going to essentially assign a hybrid or hybridized orbital to that. It's going to correspond to it. So what I have down here is I have like essentially the final answer for everything. So whenever you have a linear geometry, steric number 2, it's going to be SP, right? 2 orbitals, S and P combined together to make SP, right? Whenever you have trigonal planar, right? 3 groups. So you have S plus P, aka SP2. So 3 groups all working together, right? As we're kind of looking at the structure, right? All these are together. We're going to have S plus P, and it's going to work together to make SP2. Same thing with tetrahedral, right? S plus P, because you have 3 p orbitals. They're all going to hybridize together to assign to rearrange those 4 groups around tetrahedral. Trigonal bipyramidal, well, okay, you only have 3 p orbitals, so what can you access next? You're going to access the d orbitals. So this is what's going to explain the expanded octet rule, meaning whenever you violate the octet rule by not following it, right? It's like, you're like, okay, all of a sudden some atoms can all of a sudden have more than 8 electrons. Why? This is why. So it's the hybridization. It allows to be able to rearrange all your orbitals to be able to bond to more things. Same thing with octahedral, right? You can go to sp3d or sp3d2 when you go to 6 groups. And that's the limit, right, for this general theory. It generally goes up to 6. Anything that's 7 or 8 or more groups, that's usually when you're doing coordination complexes. That's not what this video is going to be focusing on. That's all about how do we try to do this. So, okay, what does all this explain? All right. The first thing is it explains chemical bonding through atomic orbital overlap. I can't say that enough times. I already said it 3 times. It's going to utilize hybridization to explain the Vesper geometries. So that's going to be our whole idea, right? Is to get to the shapes. We're going to be focusing on sigma and pi bonds. So we're going to be forming both those. So sigmas are usually our single bonds. Pi bonds are going to be used in double and triple alongside sigma. And the whole goal here is to minimize energy. And it's all based on that atomic overlap, right? So it's because of all those orbitals combining together, it's going to have this. You have to be able to understand how to describe bond strength, right? It's completely proportional to overlap. Sigma is always stronger than pi. And you can look at thermochemical data to back that up if you studied thermodynamics or thermochemistry at some point. The other thing is that usually this is always partnered with molecular orbital theory, which will give you a completer understanding of molecular orbitals forming, meaning this only covers so much, right? This is a basic understanding. It can go deeper and then even deeper than that. So it's kind of the idea. All right, where we're gonna go. Let's go through a bunch of different examples and try to see what else we can learn. All right, first thing is we're gonna be kind of approaching this from a theory standpoint, but also going through how to do the examples. So, all right, so if we had the first one, beryllium hydride, right? So BEH2. So the first step was that you had to determine what the Lewis structure is, right? So really quickly, you can probably see, okay, beryllium can bond to 2 different things. When it comes to looking at your periodic table, it's on the second column, meaning you can bond to 2 different things. Okay, if we were to look at how the electron configuration is in our orbital diagrams, you see they have 2 electrons in the 2s orbital. And hopefully now that you're kind of starting to see where errors are, this looks like a problem. You have 2 electrons already paired. The first thing about the theory was they had to be unpaired in order to bond. So how the heck can that bond? And it's not ionic, it's covalent is what we're talking about. Okay, so that's the isolated atom. So in order to do the bonding, right, to satisfy hydrogen, this thing is willing to rearrange itself. So okay, what's the next step? Next step was determine the steric number, right? So also your geometry. So we have a steric number of 2, aka a linear geometry, right? You can see it's 180 degrees. This is linear. So what does that mean is Sn is equal to 2 is 2 atomic orbitals are required to hybridize and turn into 2 hybrid orbitals. Okay, so we're going to take one s orbital, then we're going to take one p orbital. So s plus p is sp. Now, there's a problem, right? You see that we started with 4 lines, 4 orbitals that are all over here, right? We had 1, 2, 3, and 4. So if you start with 4, you have to have 4 when you're done. So what happened to the other p orbitals? They stay up at the top. They didn't get touched, right? So they just stay at their energy, but they're just kind of empty at the moment. So what were we going to do is we're going to fill an electron in each orbital. Because it's degenerate, we fill across. Just like you would fill a p orbital or a d orbital or an f orbital, you fill each one first. It's like I kind of say is every electron wants its own room before it starts pairing back up. So what does this allow us to do is like, okay, wait, we have an empty spot now for each one of them. So this is where the bonds can be made. So what's kind of happening here? So we combined an s and a p orbital together. So what are they going to do is they're going to hybridize and make essentially a new shape. I know it doesn't really might look like because my artwork's not the best, but it kind of combines the two together. You got to keep in mind that s orbital, even though I drew it really big, it's way smaller than the p orbital. So it's going to kind of add them together into their 2 versions. So it's going to make 2 sp orbitals. So that way it can bond both hydrogens. So we'll add them together, and that's where we get the linear shape, right? So you can see that 180. So what we can do is we can kind of overlay that with beryllium, and it's going to then bond to the s orbitals of each hydrogen on both sides. Okay, so put one hydrogen on one side, one hydrogen on the other. So we can see, okay, we have the sp orbital, and then we have the s orbitals for hydrogen. So the big thing is that depending on your professor, right, you probably have to describe the bonds. So, okay, what do we got here, right? So we got two of them, right? We have one on the left and one on the right. So is it sigma or pi? And that's the thing I think about, right? It's a single bond. So what are we going to do? Single is sigma. Okay, so we have a sigma bond. And what's attached? So we have the beryllium sp orbital is bonding, and this is a dash, not a minus or anything else, right? So it's showing a bond, and it's combining with the hydrogen s orbital, right? So they're combining together. So that's what the bond is. Now, when it comes to writing this, I've seen it written both ways. I've seen it written as hydrogen with just an S. I've also seen in some textbooks where they'll write one S. I I think it's kind of I don't really see a huge kind of big deal depending on one way or the other, as long as you're aware it's the valence level, which is 1s here, right? It's a little redundant, but you kind of pay attention how your professor or whoever's doing your grading, how they did it in class. Sn equals the 3. All right, so steric number is 3. We have 3 orbitals are going in, 3 orbitals come out, right? So sp plus p is going to make these 3 hybrid orbitals, right? So to make sp2. And when we overlap all of them, it's going to look like the trigonal planar geometry, right? So we're adding all 3 of those together because they're overlapped, right? So it's going to make a triangle. Okay, let's do it with BH3. What's happening in terms of the energy? Okay, so we have boron, right? So boron's our central atom. We got 3 valence electrons. And the first thing you're going to notice is that there's only one lonely electron. Okay, so it can only make one bond. That's not what's seen in physical data. All right, so what's going to happen to the boron? How many hybrid orbitals do we need? Well, we had a steric number of 3 was what we had. So if it's Sn is equal to 3, you're going to need 3 hybrid orbitals. So put the 3 orbitals right in between S and P. So that'll be sp2. And the last p orbital is going to be up top, right? 4 went in, 4 got to come out. You got to write them all. All right, so what are we going to do with those electrons? We're going to put 1 in each one. And now you can see that, hey, you got a spot for each of those bonds that are possible, right? All half filled. So that's our biggest thing. So what does this help you show? It actually helps show that the deficient octet is actually okay. All of them are at the same energy level. They're all filled up. The one that's all the way up at the top is like, yeah, I'm empty. I'm up here. I'm way too high to reach anyway. So it's kind of it actually helps make some sense out of some of these little trends that are breaking every rule. It's like chemistry. The rules only work at 9 o'clock on a Tuesday when you're at SPT. It's like, okay, well, that's cool. So how can we actually try to use this to work? So when we have the bonds, right, you can see that sp3 orbitals, so all 3 of them, are interacting with each of the hydrogens. So, okay, how do we describe it? We have 3 of these orbitals that are interacting. We have a sigma bond that's interacting, right, single bond. Being that if you were to kind of draw it out, you'll see that, hey, we have the boron, it's all the hydrogens. And how would we describe it? Well, okay, boron was sp2. Oh, and I don't know why I wrote sp3 there. Just notice sp2. And it's going to be interacting with the hydrogen s orbital, right? So same orbital as before, right? It's the atomic orbital because it's only making one bond. So it doesn't have to hybridize over here. It's only when it's making a double or a triple. Okay, cool. So that would be trigonal planar, and that's for BH3. Let's go on to the next. All right, Sn is equal to 4. This is when we're going to add an S plus a P plus a P plus a P orbital. So you have you have 25% S and then 75% P character here. Okay, so we have the 4 atomic orbitals are going to come out. You're going to get 4 hybrid orbitals that are going to be here at the end. And what they're all going to end up doing is you're going to add all of them together to kind of make a tetrahedral shape. So I tried my best there to make that look like a right orbital shape. That's usually not the most important thing. Most teachers you don't have to usually draw everything like that, at least I hope. But if you do, then okay, make sure you're aware of how generally they look. All right, so carbon, right? So before we had 4 valence electrons. So now we're going to be able to make the 4 bonds because we had 4 atomic orbitals. We have CF4, right? So the structure is going to look something like this. So you need 4 bonds, steric number of 4. So we need 4 hybrid orbitals. So we'll write 1, 2, 3, 4. So we have S, P, P, P. So we'll simplify that to sp3. Okay, so let's fill in our electrons. We got one in each one. And now it makes a little bit more sense. You have 3 openings for 4 bonds. Before we only had 2. It's like, how the hell did carbon bond to so many things? Doesn't make any sense. So now it actually fills in the entire picture, right? Shouldn't accept anything at face value. All right, how do we actually write in terms of describing the bonds? So you got to remember what was the last orbital for F. And that's where, if you remember, it was like 2s2, 2p5. So it's going to be the p orbital is what this is going to be bonding to, because we're making just a single bond to that. Okay, so when you draw it, right, if you have to draw the orbitals, you'd have that tetrahedral geometry for carbon. So that'd be sp3. And then you're going to try to draw your best p orbitals for each of the fluorines here. So in order to describe the bond, you're going to have a sigma. There's 4 of them. So it'd be carbon is sp3. And it's going to bond to a p orbital for fluorine, right? So actually not too bad, right? The more you kind of practice it. So this is our tetrahedral shape. Let's go into Sn equal to 5. Sn is equal to 5 and 6 is when it starts explaining octet rule violations. So when you get to the 3rd row of the periodic table, the d orbital becomes theoretically available based on quantum numbers, right? So if n is equal to 3, L can be equal to 2. Now at the 3rd row, the d orbital or the d block isn't there yet, but it exists. So okay, what can happen if we were to, let's say, look at PCl5? So I got the Vesper structure written there, right? So you can see it has a steric number of 5. So we got all these groups. So steric number is 5. That means I need 5 hybrid orbitals. I'm going to have 1, 2, 3, 4, 5. So how would I describe it, right? I got S, P, 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 and ooh, I'm out of p orbitals. So this is where we grab one from D, right? So that's going to be our new one that we add into here. So what we're going to do is we're going to simplify that to sp3d. Here, I'll make that consistent, make that green, because that's our new one. Okay, so now is this kind of complete? Well, all right. Well, how many d orbitals do I have left? Right, so there's still 4 that remain up top because we didn't touch them. And what else do we have to do with this picture? So we have to fill in our valence electrons. So phosphorus has 5. So you can see originally it can only make 3 bonds, but now we're going to be able to make a total of 5 bonds. So we're going to put 1 arrow in each of these lines. And you can see, hey, we can now make 5 single bonds. That's incredible, right? Okay, so the next thing is, right, is what was the last electron in chlorine, right? So we can complete this picture. So if you kind of remember, right, it's 3s2, 3p5. So the last one is in the p orbital for trying to explain this. So if you were to kind of draw it, it's going to look something like this, right? It's trigonal bipyramidal. So, all right, what do we got here? So in white, I have our sp3d orbitals, right? So we got the 5 of them there. So how are you going to describe it, right? You have 5 orbitals, all sigma. So you're going to describe that as as phosphorus, and it's going to be sp3d, and that's going to be bonding to our chlorine, which is its p orbital, is what we're going to be explaining as chlorine, right? So that's our entire thing. Yeah, 5 of them. They're all kind of bonding together. Let's do our last one for Sn is equal to 6. Whenever you see a noble gas bonding, it's like, wait, when did they ever bond? We were told, and especially when you first started high school chem or whenever you learned chem, is that they can never bond. But all of a sudden, your teacher is giving you these things, and you're like, this doesn't make sense. We were always told it's like everything's a lie. So specifically, when you write down its isolated atom structure, you're going to see that it has no room for any bonds. But what it can do is it can rearrange itself and satisfy all these fluorines that are around it. So let's say if I had XeF4, how would you do it? So, okay, first thing is we got to count how many groups we have, right? So we have 1, 2, 3, 4, 5, 6. So steric number is 6. So what are we going to do is we're going to draw 6 orbitals, 1, 2, 3, 4, 5. And as a result, we also will have 3 orbitals still remaining above. So what is this new orbital, right? We have S, P, 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 D, D. All right, that's confusing. Let's simplify it. sp3d2, right? So you had 2d orbitals, 3p orbitals. We'll fill it in. All right, so being that we're filling this all in, right, it's all single bonds, so everything's going to be hybridized because lone pairs sit in hybridized orbitals. So we're going to be filling across. So we got 6 so far. Then we're going to double them up. Now, does this make sense? Well, okay, let's take a look, right? One of the things we had is we had 2 double bonds. Okay, or not double bonds, sorry, 2 lone pairs. So it describes that. Then we also have 3 openings for, or sorry, not 3, oh my goodness, 4 openings for all of your single bonds that are here, right? So we have 4 openings for single bonds, and we're describing our 2 lone pairs. Phenomenal. All right, let's kind of draw it. So once again, we've done fluorine a few times now. So we have our orbitals. So let's describe them. All right, so you have 4 single bonds. They're all sigma. And how would you describe that? Well, it's xenon, and that is its sp3d2 orbital, and it's bonding to fluorine's p orbital. All right, so all that is connected. We got 4 of them. Now one question I usually get, do you have to describe the lone pairs? No, right? This very diffuse lone pair kind of sitting on top. So I kind of drew them as like, these little guys that are kind of sitting here all happy, kind of pushing everything away from it, the whole idea with this electron geometry. So this one would be octahedral. It is the electron geometry. The actual molecular shape is square planar, but this describes the electron pair geometry. Let's take a look at some examples with doubles and triple bonds and wrap this video up. All right, double bonds. So whenever we do a double, it has to be a sigma plus a pi bond to make a double, right? It's 4 electrons, so we need 2 orbitals to house those 4 electrons. So remembering, sigma is hybridized. Whenever we do pi, it's unhybridized. And pi has to be parallel, sigma is overlapped. Okay, so now that really matters when you're drawing them, meaning drawing the real shapes. All right, so the first thing is how do we kind of do this? So the first thing is you have multiple central atoms here, right? So we have a carbon, carbon, they're both central. So, but they're both going to have the same hybridization to them. So let's say if we look at one of them, we'll do the one on the left. We're going to count how many groups as 1, 2, and then it has 3, right? That entire thing on the right is one group. Like I kind of joke with my students is like, do atoms have eyeballs? And they don't, right? All they do is they sense what's around it. They're just trying to space everything around it. They want their personal space, right? So there's 3 groups. They're all going to be kind of far from each other. So, okay, we have those 3 that are there on that carbon, and it's going to be the same for the other one. So, okay, what's a steric number 3? Well, okay, so it's S plus P plus B. So it should be 3 of them. So that's going to be sp2 hybridization. And that's going to be the case for both carbons. They're both sp2 when you go through the work. All right, so you're going to write out your original electron configuration. Being that's sp2, then it means I need 3 hybrid orbitals. And that means you're going to have 1 that's going to be up at the top. Now, being that when we look at one of these, all right, how many single or sigmas do you have to form, right? So there's 1 for each hydrogen. Then we have, I know here, we'll label in red. So we have 1 for each hydrogen. And out of the double bond, remember, it's sigma plus pi. So one of those is going to be reserved for the sigma portion of the CC bond. The other one, this unhybridized one, is going to be where your pi bond is going to go. Okay. So this is where it gets a little tricky. So 1 electron is going to be shoved all the way up the top, reserved for doing the double bond that is on the structure. So let's take a look at what this thing looks like in terms of trying to draw it. Okay, so the first thing is let's draw the hybrid orbitals. So okay, we had sp2, so it should look like trigonal planar, right? We want to kind of try to make it look like a rough triangle, like so. I know I'm not the best artist, but that's okay. So we'll do it for both, right? They're both sp2. And what's connecting to those hybrid orbitals is you have your hydrogens. Okay, so that's gonna be a little circle. That's gonna be a little circle, another circle, and then another one. Okay, cool. So we have most of the structure, but how we describe the double bond? Okay, so that p orbital that's left has to be essentially a parallel orbital. So usually what I like to do is I like to draw two parallel lines, and I usually favor the y-axis first before z, but as long as it's parallel, then you're okay. Usually always goes y then z, but you can as long as you do a parallel one, you'll be okay. So okay, we have our green one here is what's going to be hybridized. So here, let me change that wording. So green is unhybridized. And the way that you can draw this really depends on who your instructor is. I personally just like to connect it with a green line. But the way that this kind of really looks in terms of drawing is that it kind of really stretches the orbital between the two. So it's extremely diffuse. I like to just connect them just with a simple little line, but like I kind of said, it really depends on how your professor has drawn it in class. So you got a pi bond, the sigma and the pi are connecting together to help show that interaction. So you got a sigma, sigma, sigma for all the hydrogens, and then you have that sigma and pi in the middle for the double. All right, so how would you describe the bonds though? All right, that's kind of the tricky part. So, okay, we got four bonds that are referencing the carbons to hydrogens. So, okay, so you got carbon, it's sp2, it's bonding to the hydrogen s, right? So we've done that a few times. Now for the double bond, you would describe it as you have a sigma C sp2 going to our other carbon sp2, and then it would have a pi bond that's C p to C p because that's your unhybridized one. So, okay, so both of these guys, this is your double, and the one on the top is going to be your hydrogens. Okay, so that's all the hydrogens. So C to H, and then your carbon to carbon. All right. Let's do one more, which is a triple bond. So whenever you have a triple bond, this is when things get a little tricky because you're not only doing a steric number, but you have to also make sure that you're accounting for whatever atoms are doing the double and the triple bond. Because even if they're only connected to one thing, because they're doing a double or triple, they have to be hybridized as well. So what do I mean by that? All right, so if I look at carbon, right, it's attached to two things. It's attached to a nitrogen and a hydrogen. So it has a SN of 2. So that's going to be sp. Now this nitrogen, on the other hand, it's only connected to the carbon and then also connected to a lone pair. So even though this is not the proper way to do geometries, you also can assign it as being next to two groups because when it comes to electron pair geometry, it's all about how many things is it connected to. It's not about the actual shape that's here. So both of them are going to assume that SP geometry. So, okay. So when we're kind of looking here, right? So let's do carbon first. So we had SP, so you're going to need two hybrid orbitals and then two unhybridized orbitals. So you'll fill in your electrons, fill in two at the bottom, and you're going to need two up at the top because remember, you need two pi bonds. So because we're making a triple. Then down here, this is going to be a sigma. One's going to be for the H, and the other one's going to be a sigma for the nitrogen. That's going to be up here. So now when it comes to nitrogen, okay, so same thing, right? So you got 2s and then 2p. So you had 5 valence electrons. So, okay, we need sp as well. So same deal, s then p. And we'll fill in our electrons. So, okay, so same idea. So we need to make sure we fill in the geometry correctly. So, all right, we are making a triple. So we got our 2 pi's, but I have a missing one, right? I had 5 arrows on the left. I have only 4 on the right. What else do I need? Well, this one has a lone pair that's on it, right? So we need to make sure that, hey, we account for that little lone pair in our structure. And then we also have room for a sigma bond and then also the 2 pi's. So it gets a little gross. All right, so because of that nitrogen having multiple, we have to hybridize. So I saved a little time. I drew the hybrid part and then I drew the parallels as well. So let's kind of show what I have. So the purple is our sp hybrid. So notice how it's linear, right? It's going in a straight line down this x-axis here, right? So you have the little lone pair with the little red dots. White is the y parallel axis. Green is the z parallel axis, right, on the other side, right? So that's going to be the other thing. Okay, so our first line, let's label. So we have our sigma bond. We have another sigma over here. Then you have our first pi double bond. And then you have another one in the back where you have a triple bond, right? So you got a one that there's a cross between the two, right? So both of those different orbitals are interacting. Ugh. All right, how do you describe it? All right, let's do the easy one, which is the carbon, the hydrogen. So okay, carbon sp is interacting with hydrogen s, and you only have one of them. Then we have our bonds for our triple, right? So it's sigma plus pi, so we need to describe all of them. Okay, so it's carbon sp to nitrogen sp. And then for 1 pi, it's going to be carbon p to nitrogen p. And then you have another pi, which is carbon p to nitrogen p. Now, some instructors, they might require you to label what's py, px, pz when you're labeling these two. It depends on kind of you, right? And how your professor's teaching it. If they are labeling it, then obviously you want to label that. Just to kind of, be complete here, right? So one of them would be like y, and then the other one would be z based on how I drew it. Usually a lot of times Z is the internuclear axis when it comes to bonding, right? So between the line down the middle. So it just depends on your class, right? If it's organic chem, usually it's always a Z. All right, let's go through the normal problem so you'll see with this. All right, let's take a look. All right, the most common problem you're going to see is whenever you're just given a molecule and you have to label what the hybridization is. So it's going to like point to an atom and you have to explain, say, hey, what is it? And it's pretty easy. It's memorizing that chart that I showed you earlier, which was, linear is sp, then it's sp2, sp3, sp3d, sp3d2, right? So in that order. Okay, so if you were to do it, right? So if we look at A, all right, so this is dopamine. So how can we try to do it? So the first one, right, you're counting how many groups, right? So we got 1, 2, 3, and then we have the fourth one that's here. Don't forget to count like that whole molecule as a group. Okay, so four groups. So what is it going to be is S plus P plus P plus P. So it's sp3. All right, if we go to B, all right, how many groups do you got? All right, so we're going to be counting here. We got the double bond leads to one, the single bond leads to the other, the hydrogen leads to the other. So this is 2. Not 2. So it's 3 total. So how would we do that? That would be sp2, right? So counting each of those different pieces. All right, C. All right, so if I look at the oxygen on the other hand, all right, we got the hydrogen, the one that's attached to the carbon, and then you have the lone pairs that are up here. So 4 groups. So once again, it's going to be sp3. Same thing with D. How do you do that one? Well, same idea. You got 1 group, 2 groups, 3 groups, 4 groups. So once again, it's sp3. So that's kind of when it gets a lot easier, is that when you look at organic chemicals, mainly it goes up to sp3. Very rarely do you see a chemical that goes beyond that because that's usually never organic. And this is usually the most common area that you'll have to know for organic chemistry is labeling, because it helps you with NMR spectroscopy, IR spectroscopy, how to be able to understand geometries for predicting what you're making. And that's the most common. The other thing that you could have too is maybe if like someone points to a bond and they're like, hey, describe that bond. So, okay, if I were to do that one, right, sigma, and you say carbon, and one of them was sp2, and then the other one would also be sp2, right? Because it's the 3 groups around each of them. So that could be another one where you could try to describe it without even drawing it, just by labeling. Okay. All right, so that's everything I had. I know it was a long one, but hopefully this helps you, right, to be able to go over all the details when it comes to hybridization, how to do this. If you have questions, please post them, please message me, reach out. And thank you so much for watching. I hope that this video helped you a little bit, and I look forward to seeing you in the future. All right, y'all, have a wonderful, wonderful day, and I'll see you all later. Bye now.